Hello everyone, welcome to the third workshop of DGSIM and FunKit. In this workshop, we are going to discuss the sequential circuits. Okay, so sequential circuits are those circuits whose output depends on the current input along with the past output. So this is the block diagram of a sequential circuit. Here you can see there is a path connecting from the output side to the input side via some memory element, and this memory element will store the past output and feed it to the combinational circuit as an input, which in turn calculate the next output. Okay. Need for the sequential circuits. Until now, we have ignored the issue of time. Also, we have assumed that our digital logic circuit perform their computation instantaneously. This is true to some extent, but for combinational circuits, in reality, time is an important issue. Even in the combinational circuits, our logic gate introduces a small amount of delay, which is in order of few nanoseconds. Also, the sequential circuits is the only thing which can store the binary data. Now the difference between combinational and sequential circuits. Combinational circuits has output which depends on only current input, but sequential circuits have our output which depend on current input as well as previous output. Combinational circuits has feedback loop, but the sequential circuit, combinational circuit has no feedback loop, but sequential circuits have feedback loop. Combinational circuits are made up of basic logic gates, and the sequential circuits are made of basic logic gates along with the memory elements. These memory elements are essentially the sequential circuits. Examples of combinational circuits are multiplexer, encoder, decoder, adder, comparator, and so on. And the example of sequential circuits are counter, flip-flop, shift registers, etc. This is the block diagram of a combinational circuits and that of sequential circuits. Here again you can see there is a path connecting from the output side to the input side of combinational circuit. This is the memory element, and this path is called the feedback path. This provides the output to the input of combinational circuits. While this combinational circuit doesn't have any feedback loop, and that's why the output depends only on the current input. Here you can see inputs are say x1, x2, x3, then outputs are f of x1 plus f of x2 and so on. Now the types of sequential circuits. Sequential circuits are of two types. One is the synchronous and another one is asynchronous. Sequential synchronous circuits has output change which can occur only at discrete instant of time. This type of circuit achieves synchronization by using a timing signal called the clock signal. While the asynchronous sequential circuits output can change at any time, any instant of time. It is clockless. If you consider this signal is called clock signal, and its value varies between 0 and 1. Okay, so the synchronous circuits can change only output at this instant of time or this instant of time. These are called active edges of a clock signal, while the asynchronous can change output at any time. It doesn't have any input like clock. Okay, so example of synchronous circuits are flip-flops, while that of asynchronous are latches. Is it clear till now? Anyone can confirm?
Yeah.
Now the memory elements. Memory elements are the circuit that can store a value for a certain period of time. Also, it can change its value depending on the input. Examples are latches and flip-flops. Latches are said to be level-sensitive devices, operate with signal levels. That will be clear within few minutes. Flip-flops are memory element device which can change condition based on the clock signal. Clock is a square waveform that I just discussed. So if you consider this latch, latches are level-sensitive devices, means it work on this region, while the flip-flops work on this active edges. Like this edge is called positive edge, and this edge is called negative edge. Negative edge means output the clock is going from 1 to 0, that's called negative edge, and when clock goes from 0 to 1, that's called the positive edge. Now there are two type of triggering methods in memory elements. One is the level triggered, or we can say level sensitive, and another one is edge triggered. Latches are pulse triggered or level triggered. Okay, like this way. If we have this part, then latches are off. Off means it will not change its output even if inputs are changed. But for the edge triggering, there are two type of edge triggering. One is the positive edge triggering, and another one is negative edge triggering. Okay, so in positive edge triggering, when the positive edge arrives, then the output, then the input will get registered. Means that input will be evaluated only at this edge. While for the negative edge triggering, the output will be evaluated at this edge, this negative edge. This is the structure of a NOR latch. This is called SR latch. Also, it is called NOR latch. Okay, yeah, if you consider the working of this NOR latch, consider this that S is 1 and R is 0. Waiting. Can anyone confirm which gates the truth table is this? Can anyone tell me?
Nor,
Yeah, no, no.
nor.
So here you can see, if any one of the input is 1, then output will be going to be 0. So if you consider this SR latch, and this S is 1, and consider this R is 0. So the output will be here 0. So input at this second latch will be also 0, and then output of this latch will be 1. So when my input is 1 1 and 0, means S is 1 and R is 0, then Q will be 1 and Q complement will be 0. That's what written here. Now if you consider the opposite case, if you have R is equal to 1 and S is equal to 0, then this will be 1, and again this here will be 1, so Q will be 0. Now in this case, when R is 1 and S is 0, the output is going to be 0 and 1. That's what written here. Now if you consider both R and S are 0, and say Q is 1 and 0. Okay, so my input here will be 0, and 0 0 will produce 1 as output, and here 1 0 will produce output 0. So again here you can see, if I have S and R both 0, then output is not going to change. Means we say that it is a memory state. So this state is memory state. Now again, if you consider 0 and 1, and here again the input is 0 0, so here 1 will be at input, and again this output is going to 0, and here 0 0 1, this output is going to 1, means again this is memory state. Now if you consider 1 and 1 as input, and here consider this Q is 1 and Q complement is 0. Okay, so here 1 1 will produce 0, and 0 1 will produce 1. Sorry, 0 1 will produce 0, but this is contradictory, because Q and Q complement should be complement of each other. And if you further analyze it, so here it will be 0, and 0 1 again produces 0. So that's the problem here. Is it clear, SR latch? Hello. Is this clear, SR latch?
Yes, Prem.
Okay. Now, if this is the another SR latch, that is NAND. It is made up of two cross-coupled NAND gates. Now, again, if you consider this input as 0, and 1 minute, let me write good table of NAND gate. If you consider S as 1 and R as 0, so here you can see in the truth table of NAND gate, if any one of the input is 0, then output is going to be 1. So here it is clear that output is going to 1, and again 1 1 will produce output as 0. So for S comma R is equal to 1 comma 0, output is going to be Q is 0. Okay, so if S is 1 and R is 0, then output Q is 0. Now if you consider another case, uh, here reset is 1 and S is 0. So here you can see if any of the AND gate has 0 input, then the output will be 1. So here 1 and 1 1 will produce 0. So when R is 1, that Q is going to 1. When R is 1, Q is going to be 1. Now if you consider 1 1 input, and say Q is 0 and Q complement is 1, so here 1 1 1 will again produce 0, and here 0 1 produces 1. So this state is called the memory state. It is memory state because the old value is getting preserved. So again, if you consider 1 1 and this 1 1, both are memory states. Now if you consider 1 and 1 as uh, not 1 and 1, if you consider 0 and 0, and say your Q is 1 and Q complement is 0, then 0 0 output will be 1, and 1 0 the output is going to again 1. But this is again contradictory because Q and Q complement should be complement of each other. That's why this state is called the forbidden state. Now one thing left. Can anyone tell me what will be the output of SR NOR latch when S is 1 and R is 0? What will be the output of NOR SR latch when S is 1 and R is 0?
And Q will be 0 and Q dash Q will be 1, sorry, and Q dash will be 0.
Yes, Q will be 1 and Q dash will be 0. And what will be the output when it is NAND latch?
0 1.
0 1.
0.
So basically, SR NAND latch and NOR latch both are complement of each other. Means when S is the set, here S complement is set. Yeah, now this is the SR latch with enable input. Here you can see there are two extra NAND gates, and there is third signal that is called enable. So if you consider this enable as 0, then here 0 and here S. Can anyone tell me what will be its output?
1.
Yes, it will be 1, and here again this output will be 1, and 1 and 1 are memory state.
Memory.
Correct? Yeah. Now if you consider enable as 1, then this will act as buffer, not buffer, it will act as not gate. And if you remember, this is S complement and this is R complement. So if you input here s and here 1, then the output will be going to s complement, and this s complement and s complement will cancel each other. Means when enable is 1, then this will act as a SR NOR latch. So here you can see, if enable is 1, then for SR latch 0 0 is the uh, for SR latch 0 0 is the no change, means memory state, and 1 1 is the forbidden state. And when S is 1 and R is 0, that's called the set state. Set state means Q is equal to 1. And when S is 0 and R is 1, that's called the reset state. So basically here this enable input is controlling the behavior of this latch. This enable input causes the latch to work or either not work. Not work means memory state. And one more important thing here is that this is the indeterminate state. Here if you see carefully, S and R are both complement of each other. Means when S is 1, then R is 0, and when R is 1, S is 0. And if by mistake both S and R will become 1, then that will be going to cause a problem to us. But we can avoid it by taking R as complement of S. That's called the D latch. Here you can see this is R, and this is S, and this is R. Here you can see R is equal to S complement. So here our 1 comma 1 input will get eliminated. So if you consider the working of this circuit, if my enable input is 0, then again here 0 and here 0. So my output here will be 1 1, and 1 1 for a NAND latch is its memory state. So when enable is 0 and D is don't care. Don't care means it can be anything, either 0 or 1, we don't care for it. So it is going to be memory state, or say no change state, memory state. Now if enable is 1 and D is 1, then 1 1 will cause 0 as output, and here 1 comma 0 will produce, here it will be 1. So 0 1 will produce 1 as output, and again as this is 0, Q will be 1, and again 1 1 will produce 0. So when D is 1, Q is 1, and when D is 0, see this case, when D is 0, this is 1, and this is 1, so this will be 1, and then Q complement will be 1. So 1 and 1 will produce Q is equal to 0. So when I have D is equal to 0, that's Q is equal to 0, and it is called reset state. Reset state means the output is 0, and the set state means output is 1. Is it clear till now?
Yeah.
Now this is the JK latch. Here again you have enable input, and when this enable input is 0, so here output will be 1 and 1, and 1 and 1 is memory state for a NAND latch. Here this is the SR NAND latch. So 1 and 1 are its memory state. So here when enable is 0, Q will not change. So generally we don't care for this enable is equal to 0, and we see it's working when Q enable is 1. When enable is 1 and J and K both are 0. So again, if any of the input of a NAND gate is 0, then output is going to be 1. So here also output will be 1, and again 1 and 1 is the memory state. So when enable is 1 and J and K both are 0, then my output will not change. So that's the, here you can see that see, suppose this is Q plus, then my next state is going to be initial state, means Q is equal to Q naught, there is no change. Now if you consider another case, enable is 1 and J is 0, sorry, J is 1 and K is 0. So here output will be 1, and here the output will be 1. And if you consider this as 0, means Q is equal to 0, q is equal to 0 means q complement is equal to 1. So 1 and 1 will produce 0, and which again produces q is equal to 1. Means if you consider anything, either q is equal to 1 or 0, you will get q is equal to 1 when j is equal to 1. Now if you consider another case, j is equal to 0 and k is equal to 1. So here output will be 1, and if you consider this q as say 0, then here this q is 0. So here uh, input will be 0 and output will be 1. So 1, and here it was 0. So 1 and 0 will produce 1. That's correct, obvious, because q is equal to 0. So q complement will be 1. Means when j is 0, then q will be 0. Here q is equal to 0 when j is equal to 0 and k is equal to 1. Now if you consider another case, 1 comma 1 input, so say enable is 1 and j and k both are 1, and assume that this q is equal to 1 and q complement is 0. So here input will be 1. So 1 1 1 will be input this to this second NAND gate. So here output will be 0, and here this part output will be 1. As you can see, when my q complement was 0, it converted into 1. Similarly, if you consider for this upper part, this q complement was 0, so here it will be 0, then it will produces 1, and as this becomes 1, so here 1 1 it will produce 0. Means when j is equal to 1 and k is equal to 1 and enable is equal to 1, q will become q complement. Means the output toggles. Means if it was 1, it converted into 0, or if it was 0, it will be converted into 1. That's called toggling. Okay. Now we have another type of sequential circuit, that is called flip-flop. Basically, latches are level triggered. Any change on its input is seen at output only when enable is equal to 1. This caused the synchronization problem. The solution of this problem is that we can use flip-flop that can change its value only at the specific time, and that specific time is called the clock edge or the active edge. Basically, we have a SR flip flop, D flip flop, JK flip flop, and T flip flop that we will see soon. Uh, yeah, the same thing here. We have two type of edge triggering in flip flop. One is the positive edge trigger. Means positive edge means whenever the clock transitions from 0 to 1, then our output will be get evaluated based on the input. And we have another type, that is negative level triggered, and for negative level triggered, output will change in accordance with the input at the negative edge of the clock, and that will be stored for the rest of duration. And here you can see this is the negative edge. Means that clock signal is going from 1 to 0 at that time. Now this is the SR flip flop. Its working is similar to the SR latch. Only thing is that it has clock input. This C symbol is used for the clock input, and you can see there is a arrow. This is the block diagram of a SR flip flop. And if it has bubble on it, then it's called the negative edge triggered SR flip flop. If you remember SR latch, it was 0 0 0 1 1 0 1 1, and output was 0 0 means memory, and 1 1 was forbidden, and for this 0, and for S1, that's R. So this is the same for the SR flip flop also. Only thing is that output will be evaluated at only active clock edge. So this is represented by this arrow. This means that it is positive edge triggered, that is active edge has been arrived. So we generally when this active edge arrives, that input will get evaluated. Here my S is 0 and R is 1. So output will become next output. Thus Q t plus 1. This is called the next state, and this Qt is called the present state. Is it clear?
Yes, Bhaiya.
Okay. Now this is the D flip flop. Here again, this is the block diagram of a D flip flop. D flip flop has two input, D and the clock input. And here this is the negative edge triggered D flip flop. And if you remember the D latch, it was like when D is 1, output is 1, and when D is 0, output is 1. This is called a transparent latch because the output is just the input is just reflected on the output side. Here it is the same thing. If I have active edge, then it means at active edge, if my at this edge, if D is 1, then output is going to be 1, that is a steady state. And if at this edge D is 0, then output is going to 0. Now the JK flip flop. JK flip flop is also JK flip flop have same working. The only thing is that should be evaluated on the positive edge. So if not positive, it can be negative. I was mean to say that it's the active edge. At the active edge, if J is 0 and K is 0, then there will be no change in the output, and that is called the memory state. And when J is equal to 1 and K is 0, output is going to be 1. And when J is equal to 0 and K is equal to 1, output is going to 0. And when J is 1, K is 1, output is going to toggle. Toggling is very important thing that we will see next. Uh, yeah. Next we have T flip flop. T flip flop is very simple. Like here, I have shown the example of negative edge triggered T flip flop. The output of say here that's the clock, and it has the active edge. When active edge arrives and the t is 0, then output is going to be same, means output will not change when t is equal to 0. And when t is equal to 1 at the active edge of clock, the output is going to toggle means complement of initial state. Okay, so here we can write q plus is equal to q uh, uh, 0 for t is equal to 0, and q plus is equal to q naught means initial q complement. That's for t is equal to 1. This is the t flip flop. Now the asynchronous reset and the set. Some flip flop have asynchronous inputs that are used to force the flip flop to a particular state independent of the clock. The input that sets the flip flop to 1 is called the preset or reset. The input that clears the flip flop to 0 is called the clear or reset. Basically, this is used when power is turned on a digital system. The state of flip flop is unknown. The direct inputs are useful for bringing all the flip flop in system to a known state prior to the clocked operation. Uh, okay, this is the this is the problem which you have to do now. Which of the function the following circuit performs? You have around you can take 4 to 5 minutes and tell me what is the nature of this circuit. Are you people doing it? Hello. Hello, can you solve this problem? Anyone? You can take 4 or 5 minutes. That's okay. Wait a minute.
भैया एक बार फिर से क्वेश्चन लिखा.
Can anyone make it? If you are not able to do, you can leave it as a homework. Is it fine for everyone? At least say yes or
Yeah.
no. I am leaving it as a homework problem for you. Okay?
Yeah, cool.
Okay. So from here, Sunny will be taking this workshop. Sunny, you can continue. Sunny, you can continue.
Now we will be talking about master-slave flip-flop configuration using latches. In this, you can see there are two D latch, one master and another one slave. As you can see the connection of the clock, clock in this, the master latch will only work when the clock is high, and the slave latch will only work when the clock is low. Suppose we take d is equal to 1, then when the clock is high, then y will be equal to 1, but the q will not update as the slave latch is currently not working. As soon as the clock goes from 1 to 0, the slave latch will start working and the q will become 1. So we can see when the clock transitions from 1 to 0, then only the q is updated. This means that this is negative edge triggered D flip flop. For making positive edge triggered D flip flop, we just have to add not get here. Any questions? Hello.
Yeah, you can continue.
Now we will be talking about characteristic table and excitation table. For this, we will take an example of JK flip-flop. As you have studied the truth table of JK flip-flop, we will derive that characteristic table from the truth table and excitation table from the characteristic table. As you can see in characteristic table, the variables are Qn, J, and K. For this, when the value of J and K is 0, the present state is equal to the next state, which is also 0. When J is 0 and K is 1, then the next state will be 0. And when J, J is 1 and K is 0, then the next state will be 1. Similarly, we can fill all the details of the next state in the characteristic table. For excitation table, we have variables as present state and next state, and we try to find the inputs of the flip-flop. The excitation table can be filled with the help of the characteristic table. Let's see, when present state is 0 and next state is 0, then we see this region that J is 0 and K can be either 0 and 1. That's why here J is 0 and K is don't care. For second one, present state is 0 and next state is 1. It's this region. Here J is 1 and K can be either 0 and 1. As you can see, J is 1 and K is don't care. Similarly, for 1 and 0, J is don't care, K is 1. And for 1, 1, J is don't care, K is 0. These are the excitation table of different flip-flops. This can be easily derived using characteristic table, which can be found out by using the truth table. For better understanding of characteristic table and excitation table, we will try to implement SR flip-flop from JK flip-flop. Sorry, we will try to implement JK flip-flop from SR flip-flop. For this, as we can see, we are given SR flip-flop and we require JK flip-flop. We have to draw the excitation table for the given flip-flop and characteristic table for the required flip-flop. And as both are currently drawn, you can see from the excitation from the characteristic table for the JK flip-flop, we can find the values of S and R using the present state and the next state with the help of excitation table. As you can see in the first row, Qn is in 0 and Qn plus 1 is also 0. From here, we can see S is 0 and R is don't care. In the second row, Qn is 0, Qn plus 1 is also 0, which is same as above, 0 and don't care. In the third row, Qn is 0 and Qn plus 1 is 1, which is the case here, which implies S is 1 and R is 0. Similarly, all the details in the table can be filled, and we have to find the values of S and R by drawing K-map using the variables Qn, J, and K. Here it is done the same. As you can see, the S comes out to be Qn complement J, and R comes out to be Qn K. So this is the figure of implementation of JK flip-flop from SR flip-flop. As you can see, don't ever try, as you can see here is Qn bar. Don't ever try to take Qn and do its complement for this purpose. Always take Qn complement from here whenever the equation is required. For better understanding of excitation table and characteristic table of every flip-flop, try doing this as your homework. Do you have any questions?
No, Bhaiya.
Next, we come to the state diagram. It is the graphical representation of the information present in the state table. State of a flip-flop is represented by the binary numbers present inside a circle. Transition between states is indicated by directed lines connecting the circles. The directed lines are labeled by two binary numbers separated by a slash, where former is input and latter is output. State table consists of present state, input, next state, and output. Present state section shows the states of flip-flops at any given time. Input state section gives a value of input for each possible state. Next state section shows the states of flip-flop after one clock period. Output section simply gives the output corresponding to each present state. For to better understand state diagram and state table, we are taking an example. As you can see, inside the circles, there are states written. In this state diagram, there are four states: 0, 0, 1, 0, 1, 1, and 0, 1. This is input, and this denotes output. For the state 0, 0, when input is 0, output is 0, and the next state is 0, 0. When input is 1 and output is 0, the next state is 0, 1. For state 0, 1, we can see when input is 1, output is 0, and next state is 1, 1. And when input is 0, output is 1, next state is 0, 0. The same is represented here by the state table. You can see the present state is 0, 0. When input is 0, next state is 0, 0, and output is 0. When present state is 0, input is 1, then next state is 0, 1, and output is 0. And for this 1, 1, when input is 0, next state is 0, 0, and output is 1. And when present state is 1, 1, input is 1, next state is 1, 0, and output is 0. We can see that from here, if we are given a state diagram or state table, we can draw draw each. If one is given, we can draw the other easily. Now we are going to talk about state reduction and assignment. State reduction method is used for reduction in number of flip-flops used in sequential circuit. State assignment method is assignment of some binary values to states in such a way to reduce the cost of combinational circuit that drives the flip-flop. One thing I might like to add, as the states are mentioned by two binary numbers, then the number of flip-flops required to implement such a circuit will be 2. Now for the example of state reduction and assignment. As you can see, there are A, B, C, D, E, F, G states present. And we would like to reduce the number of states in order to reduce the flip-flops and complexity of the circuit. As you can see in this circuit, present state G and E have same next state AF and same output 0101. From this we can say E is equal to G, and we can eliminate the state G. Also from the table we can see state D and F have same next state EF and output 01. Therefore we can eliminate the state F. As you can see, the reduced state table is given here. The state assignment is nothing but binary numbers to the state represented by alphabet. Here the state assignment for A will be 000, B will be 001, C will be 010, D will be 011, and E will be 100. The the state table here is denoted by the state diagram. To design procedure for clock sequential circuits. First of all, we will be given either a timing diagram or state diagram. Then using that we have to obtain the state table. This is the first and most important rule. Then we have to reduce the number of states if it can be reduced by state reduction method. If required, we have to do state assignment. We have to determine the number of flip-flops required and assign a letter symbol to each. We will be able to determine this using the binary how many binary numbers are required to represent the state. We can choose the flip-flops, either we can choose T, D, T, or JK flip-flop. We have to derive circuit excitation and output tables from the state table, obtain the expression for circuit output and flip-flop input, and then implement the circuit. Let's take an example. Here, this is the state diagram, and we are making the state table using the state diagram. The first state is 00. When the input is 0, then the next state is also 00, and then the input is 1, the next state is 01. For state 01, when input is 1, then the next state is 01, and when input is 0, next state is 10. Using this we can form the state diagram. This is the state diagram in the previous slide. Using the excitation table of JK flip-flop, we can fill the columns J, K, JB, and KB with the help of the QA and present state and a next state given. As you can see here, QA is 0, QA plus is 0, which from the excitation table we can see J will be 0, and K will be don't care. Similarly, we can fill all the table, all the columns of this table, and then using K-map, we will try to figure out the value of JA, KA, JB, and KB, and the variables will be in terms of QA, QB, and X. Here, here it is done. The value of J, K, JB, and KB will will come out this after solving through K-map, and using this we can implement the circuit. See here, J is equal to QB X bar. And K is equal to BX. Using this, we can implement the circuit. Do you have any questions? Has everyone understood?
Yes, Bhaiya.